Our next speaker, invite him to the podium. So I used to be, before I was in a stat department, in a psychology department. There was always a joke, which was that if you looked at people interested in perception, they weren't very perceptive people. People who studied memory didn't have very good memories. People who studied rational thinking didn't tend to be very rational and so on. So people tended to study things they weren't good at. And I don't think that holds in statistics, and here's a counterexample. So here's one of our world's experts in dynamical systems. And I think you'll agree that Mike's a pretty dynamical individual. Whether he's stationary, I don't know, probably not. Certainly nonlinear. Whether he's predictable, I let others make that call. Anyway, we're delighted to have Mike give the second ISBA lecture on Bayesian foundations. Again, this will be an hour and 15-minute slot, questions afterwards, and then we'll have a break for coffee.
Okay, well, thank you, Michael, for the introduction. And thank you to the organizing committee for the invitation. And hello, Kyoto. Hello, ISBA 2012. Glad to be here. Been looking forward to this meeting for a few years. Is everybody comfortable? Is everybody warm enough? So I was invited to give one of the foundation lectures, and as part of the invitation, I was asked to give a sort of Valencia old-style tutorial overview, which is what I've put together today. And a tutorial overview should start with at least some allusion to where things began. I'm talking about state space modeling, and it's basically the 50th anniversary of two key papers. I'm sorry, trigger happy here. Two key papers back at the beginning of the 1960s by Jeff Harrison and Rudy Kalman, coming from very different perspectives. In the one case, very subjective Bayesian modeling in commercial environments, time series problems, where time adapting to change in time was the essential of forecasting accuracy. And in the other case, a very non-Bayesian engineering perspective in control theory and control systems, but utilizing the machinery of Bayesian state space modeling. There are a lot of other people and a lot of other things that were happening around the same time that are all ingredient and are all part of where the world of dynamic modeling in time series, spatial systems, and other kinds of contexts has evolved from. But these were really what I identify as the essential people who kicked it all off. So we're talking about state space models. And we'll be looking at some pictures from examples from business and finance, where I think Dennis Lindley in the late 1980s remarked that the state space modeling has become, at that point, really the most important practical success for Bayesian thinking. This was pre-MCMC, of course, where we were still doing calculations on the backs of envelopes. So business and finance, we'll be talking about the physical sciences, we'll be talking about biological sciences, we'll be talking about a little bit, at least allusions to more recent and current kinds of applications in dynamic network modeling and in computer modeling, where these good old 50-year-old ideas and methods that are based on those ideas are really driving creative, challenging applications. So some of my slides will have at the top the term foundation. It's a foundational lecture. I'm really talking about concepts that I regard as foundational and that are foundational to this particular field. The key concept is time as a covariate, that stuff changes in time, and you ignore that at your peril. So here's a stylized model. I do apologize for this, it's jet lag. Here's a stylized model where we have some data in time, possibly with some regression, where theta here represents a regression parameter vector. And the parameter is changing in time in some way. This is a mnemonic for more elaborate models that you might use and that people do use. And if you have such a circumstance and you ignore the time variation in the parameters, then all of the variation you see about the regression gets lumped into the error. So you inflate your errors of unpredictable pieces of the model. You degrade your forecasts. You realize forecast uncertainties that are just bigger and bigger than they should be. allowing for change in very simple ways often, partitioning variation by recognizing time as a covariate is really the fundamental concept, the foundation of state space modeling. So as an example, and this is a textbook example that goes back a number of years to an earlier textbook of ours, two time series, sales and a predicted market that share similar patterns over time. And if you simply look at a y against x plot, you'd be tempted to fit a regression. And of course, if you then bring in the time covariate, you see a slightly different picture. Up here, the little crosses are the sales data, and you see an increasing parameter regression relationship. If you ignore it, then you're tracking one-step forecasts along here. You're doing a very poor job in forecasting. Your residual variances lead to inflated forecast variances. Whereas by comparison, if you recognize it and even do very simple things, then the model will adapt and track the time varying coefficient, improve forecasts, reduce forecast uncertainties, and so you win out on both counts. So time is a covariate. Always worth considering time as a covariate if time is at all in the context of the problem for these kinds of reasons. Second foundation, and that example leads us into this, is very naturally in time series, one is involved in sequential analysis. You model sequentially in time. You look forward in time as you think about how the process that you're trying to understand is evolving. State space models, this is a linear Gaussian sort of framework to begin, of course, are very natural, very naturally looked at in a sequential format. So here we have a signal in noise. The signal is a dynamic regression where the regression vector or state vector, it's a state space model, undergoes some Markovian evolution through time. A very general class of linear models. It's naturally a very highly structured graphical model, but the key point is that it's a sequential view. You're interested in looking forward and refining your description of the process that you're looking at sequentially. The sequential context not only leads naturally into forecasting sequentially, which is often a goal, and learning sequentially about time-varying structures, but also the opportunity to intervene, to take today's prior and modify it, to intervene as new information comes in, to change the model prospectively based on information external to the model to date. Maybe I'll stop using this. Okay. Foundation number 3, model composition. Very similar idea. We build regressions out of collections of predictors. We put them together. We piece them together via composition. Sometimes we call it superposition. So a signal may often be represented as a sum of signals, which combined give us the predictable part of the model. And model composition very naturally looks at each of these signals as themselves represented in terms of dynamic models of one form or another. So C indexes components, a component of an overall superposition process that gives us a dynamic model. So continuing in the context of business and commercial kinds of applications, which is where this all really began, there are various kinds of components that we can entertain. Simple linear trends, simple seasonal patterns. Here we've got a periodicity of some kind, which is represented in terms of a noisy sine wave for one component. The green part simply extrapolates. This is what you would predict as a mean. Components that are damped versions of that processes may decay when an external stimulus is taken away. Local trends, they may be quadratic or cubic interpolators or simple local levels. Regressions on independent variables that appear with dynamic coefficients. And time series components, residual autocorrelated processes that describe structure in the process that none of the above do. And when you put them together then, you get a more elaborate model for the overall time series that has those component structures built into it. And this is very key in modeling. It's very key in all modeling. It's particularly key in time series modeling. So back to the commercial and social economic context, in a sequential format or looking back at historical data, a key point is intervention. Thinking about today's posterior as tomorrow's prior, not as an immutable prior that then feeds into the next stage of analysis, but as part of an analog way of thinking about the data in its context. And being open to intervention as new information comes in is really key. So here's a time series. Again, it's one of our textbook examples of sales data with a particular little model where we're interested in and being concerned about departures from a model form that require intervention. The intervention can be feed forward. We learn something, we want to intervene, or feedback. We see something we don't like, doesn't fit the model, let's do something, let's expand the model, let's add some components, let's modify the current posteriors as they are going to become tomorrow's priors. So in this example, I've now represented the data as points, and you can see a very simple, plausible sort of model, locally linear interpolator, with some events that require some form of intervention, whether feed forward or feedback. 2 or 3 events are simply apparently outliers. There may be information that would allow us to explain or anticipate them, or certainly react to them once we observe them. 2 or 3 events that may be modeled as changes in the structure of one or more of the parameters in the state. Again, that we could anticipate with the requisite information, or that we might simply respond to after the fact. And doing that in informed ways that respect Bayes' theorem is really part and parcel of a more holistic dynamic modeling system when one is interested in forecasting. And this is simply a representation of one-step forecasts when appropriate kinds of interventions are incorporated. Intervention can be thought of technically, and this is an important slide, in a number of different ways. We're all very familiar with model averaging and model mixing. And since the 1960s, model averaging and model mixing has been de rigueur in dynamic model analysis certainly in commercial applications. So let's now imagine a class of models indexed by M, where at each time now we're seeing data, we're running the models in parallel, and updating, if you like, an unnormalized posterior probability on models as we go through time, modifying what we thought yesterday by what we see today in terms of the predictive density of today's observation under each of the models. Here's an example. This is actually an example from an econometric application where we've got 6 competing models, or 6 models running in parallel, a bank of models, where for some periods of time, the purple model indexed number 5, has an appreciable probability. And then clearly there's some data here that leads to a fairly abrupt switch to favoring a red model, model 3, and then eventually a different model will come along and have a higher probability later on. So here we've got a collection of models that are being mixed up by posterior probabilities for inference and forecasting. And this simply represents what we all know today as Bayesian model averaging. Some people will say BMA, which is the acronym that began to be popularized in the 80s. Whereas back in the 1960s, in the early 1960s, these ideas were being used both in commercial applications and in engineering applications. Back to intervention, a different kind of mixing, of model averaging and model mixing is usually relevant. There, it's not a question of models running in parallel and being weighed against each other with posterior probabilities that adapt to the data, as much as thinking about at each time there are various possibilities that might happen. So again, with the same example, we could imagine nowadays a traditional way of modeling outliers is to use something like a mixture, a 2-component Gaussian mixture where one component allows for the outliers. So there's 2 possible models, but that's 2 possible models at each time point. And if we look at the change points in this data, we might adopt a very similar strategy for modeling change points. And it may be selective. It may be that there are various components of the state vector that we may expect or anticipate are subject to abrupt changes. And then we'd be thinking about the same kind of mixture strategy there for possibly several subparameters. So this is mixtures, again, for switching mechanisms, for outliers, for automatic intervention in a dynamical model context, which again is all part of the historical panoply of methodology. So sequential learning. Just to sort of complete the picture before we come to some more examples. This is another textbook example where we're looking forward in time We've got a model that it's composed of several components. There's a trend, there's a dynamic regression, there's a seasonal pattern. It's commercial sales data in a particular context. And what we're doing here is tracking the data, and at this time point here, we've seen 10 data points. We're forecasting ahead. This is some notional forecast intervals. And because we know the data, I've plotted them on the plot as blue. And here we are tracking the coefficient of the predictive variable. And as we come through time, we're learning about this parameter. It's changing. The posterior intervals won't degenerate because it's changing through time. We're open to intervention, so as we go ahead a few time points, as we see departures from the model, we may have a mixture structure, we may be using other forms of informed intervention. We're allowed to step in and change posterior distributions in order to reflect and adapt to unforeseen forecast errors. At each time point, we're forecasting ahead, asking questions about what might happen. We do that by simulation, of course, these days, a great deal. In simple linear systems, it's analytic. And then as we go through time, to the end point, we're interested in time series analysis. So we'll distinguish that term from the forward sequential updating learning analysis, the adaptive learning, where we're more interested in looking at what is happening locally and how things are changing and anticipating change because of forecasting goals, to the looking back, the retrospection, the analysis of what we've learned and how we've learned it, and how what we have learned will help us understand how we might modify the model for the future. So here, having tracked all the way through time, we can then retrospectively update all of the relevant posterior distributions for the historical trajectory of the coefficient that has changed over time, subtly, and also, in this case, the variance of the residual error, which at this couple of points underwent some shocks that increased it, as we saw forecast errors that were unexpectedly large. Model composition has a reciprocal, model decomposition. So we build models out of components. And by the same token, when we've built a model, and I'll show you a couple of examples, very often we're interested in components. We're interested in taking a model, a state space model with a multidimensional state, and decomposing the signal in that model into potentially interpretable and actionable components. And this is a second key aspect of this idea of breaking things apart. So let's take a particular subclass of dynamic linear models. The particular subclass here, we've got some data, that's the signal X plus error. The particular subclass here has these matrices, the regression matrix, if you like. This is the regression parameter, which follows a state space model. And the Markovian transition matrix, the F and the G here, are time invariant. They don't have a subscript T. We sometimes call these time series models. And the reason we call them time series models is that all linear time series models, all linear Gaussian time series models, those of you that know about time series know all about autoregressive moving average processes. They're special cases. There are other special cases. So in a very real sense, all traditional linear time series analysis sits inside state space models. And Bayesians have been doing traditional time series analysis without knowing it for many years as a result. On the foundational concept of decomposition then, the key here is that in any such model, one can take this signal, this is just theory now, theory of differential equations or difference equations, and break it down into a series of components such that they sum to give us the signal. And these components correspond to the eigenstructure in this matrix G that defines the model. Components, sorry, I skipped ahead a slide again. Components can take one of three different forms, or several forms. Depending on the eigenstructure of this matrix G, if there are unit eigenvalues or replicate eigenvalues, one gets components of the signal that give you a whole range of possibilities: linear, quadratic, cubic, polynomial trends that are local trends. The coefficients change through time, but they represent trend terms underlying this signal. Other components of the eigen decomposition of the model give us traditional autoregressive type components of two flavors. Short-term first-order autoregressive process, so this is an AR coefficient, representing structure inside the signal that is predictable in the very short term. And second-order autoregressive processes, not quite. This happens to be an AR process itself, but for all intents and purposes, this is an AR2, which are such, the parameters that define it, the phi parameters here are such, that these generate what we call quasi-cyclic processes. So they think about them as sine waves with a fixed wavelength, but whose phase and amplitudes vary through time. The dynamics of the model up here feed through to define these time-varying processes as directly as components of the signal. This has been enormously important in a number of areas of science and engineering over many years, and one of the reasons it's been important is that it extends to really the full class of dynamic models. So this is the same slide. The only difference now is I've put back my time indices T on the F and G matrix. The same general story holds, that this signal decomposes as a series of components, which are now a little more local in the sense that there's more time variation because the eigenstructure associated with the overall model is now time varying itself. The same general components for trend and potentially seasonal components arise, and importantly now, the autoregressive components, both the short order AR1s and the quasi-cyclic AR2s arise with a difference. And the difference is simply that this time index, this time variation, feeds through into time variation in the parameters of these processes. So we get time-varying autoregressive processes of order 1, representing often just residual noise that is unpredicted by other components in the model. But when we understand it's represented this way, we understand there is predictive ability in the short term. And now AR2-like processes in which the coefficients are themselves time-varying, so these are time-varying amplitude and phase sine waves. But in addition, because of the time variation in the phi parameters, the frequency, the wavelengths are now time-varying. So this gets us into the whole business of time domain modeling of time frequency structure, where the frequency content of signals can vary in time, as well as the amplitude and the phase of those signals. Two example models that are used often with a view just to then exploiting this decomposition theory. The good old 100-year-old autoregressive model, one particular representation in a state space formulation, there are several others, is this particular form here. So an overall signal is regressed on the last 20 values of the signal. In a DLM framework, it would be a latent signal. Y is this, plus some other components, plus measurement error. And this theory then tells us, this decomposition theory then tells us that this signal theoretically breaks down into the superposition of several sub-processes. Some short-order correlated processes, little AR1s, and some quasi-cyclical processes of varying wavelengths. There may be several of them. The more general version then has time-varying parameters, so the only difference, it's the same slide, but again, I put T's on the phi parameters, and in the state space formulation, that puts T's on the parameters in the first row of G. The same story holds. The only difference now, again, is that when we look inside these component processes that this overall state space model theoretically has built into it, we see that there's the ability to represent time-varying residual component structures, AR1s, with time-varying short-term autocorrelations, and time-varying frequency content in the signal at different wavelengths that may vary slowly, in some cases not so slowly over time. So the kinds of applications that this has been very useful in tend to come in from the natural sciences and engineering, a little bit in the biomedical sciences. a few examples. Problems where we're interested in questions like this. We're interested in characterizing the process. We're not interested in forecasting it necessarily. We want to understand frequency content. We'd certainly like to understand change over time in frequency content at different frequencies. We'd like to know if there are patterns that are predictable in the sense of cyclicity, periodicities that may be sustained into the future in some kinds of applications. So here is an example that we've studied and others have studied a number of times of a time series that's inversely related to northern hemispheric temperatures, global temperatures, going back from now over the last 2.5 million years. And you can see some periodicities in there that are well known, simply related to the Earth orbital dynamics, that have a major influence on climate, including the ice age cycles of various kinds that really are the key pieces of this data. So when one fits a state space model, and the state space model here is a trend, a locally varying trend, and here's an estimate of the trend. Temperatures are increasing over the 2.5 million years. And 20-dimensional signal, it's simply an empirical representation of the signal. There's no attempt to model specific components at different frequencies. It's just an encompassing model. And then, of course, measurement error. This is an extraction of components using this decomposition theory. Just 3 or 4 of the components ordered in terms of their wavelengths coming down, and all on the same scale, so you see the relative contribution that they give to the overall data as a result. And if you look at posterior distributions for wavelengths, you'll see that they live they cover the ranges of Earth orbital dynamic periodicities that are theoretically well known. This is the data with the trend simply superimposed. Let's look at this picture. What we have here is an investigation of the wavelengths over time. This is a time-varying model, so each of these is a quasi-periodic process with a time-varying wavelength. Well, in fact, they look pretty stable. They're color-coded to correspond. They look pretty stable. But at this time point, and there's a faint dashed line at about 1.1 million years here, there's a funny switch. And what happened there is that at that time point, there was an inversion of the dominance in terms of the estimated amplitudes between the first 2 components. This is a nice example of the use of these models, and that's another nice example. And this fed in the early 90s to the conversations that were ongoing about changes in ice age cycles and whether there were discrete events about 1.1 million years ago in the orbital dynamics of the Earth that somehow ruptured the cycles and simply changed the patterns that had been evident before. And you see that in these components. You see the greater amplitude is then much less predictable after this particular time point, whereas this component goes through a few thousand years of interesting behavior, but becomes a dominant waveform. There's no change point modeling, there's no intervention modeling, there's no mixture modeling. It simply comes out of the slowly varying nature of the parameters that these models have built inside them. Second example context, and this has been very well explored over the last several years, very active area current, EEG studies and other areas of neuropsychiatry. So here we've got electrical fluctuation measurements on one point on the scalp of a patient undergoing treatment for undergoing a brain seizure that's been induced under various treatment to understand response to electroconvulsive therapy. And this is a really nice example of why this particular class of models that I just exemplified in the oxygen isotope data are really very widely used. So in the early part of the seizure, there's very high amplitude fluctuations of whatever wavelength is implied by the red plot. And as you go through time, the seizure changes. Certainly the amplitude is very variable, and it's tailing off as the seizure ends over here. But you'll see the same section of the same length over here, you see a longer wavelength. So we see time-varying amplitude and clearly phase, but we also see time variation in the frequency content, in the wavelengths of patterns underlying this data. So this is purpose-built for these kinds of models, this particular time-varying autoregressive state space model. And here's, for one of these patients, the same decomposition, now also with the data on the plot. So this is the beginning of the seizure over here, and it plays itself out and then dies away, and this is normal resting brain behavior. And some of the components that just simply emerge out of the decomposition theory are brainwaves. They're identified in terms of their estimated wavelengths with frequency bands. You can't see them, well, probably from the front you can't see them, in the delta, theta, up to the high frequency wavelengths that are identified with network communication activity in the brain. So this is an interesting kind of application where these models get used to characterize, just empirical characterization of the data, pull out inferences on what are interpretable processes, and then look at them in more fine detail. And so what we have over here is, for this data set, the blue curve represents estimated wavelengths of these three sub-processes that were pulled out going down here. This is the wavelength scale. So we'll see here more variation in the wavelength over time than we saw with the climatology data. As the seizure plays out, there's quite erratic behavior at the end. Overlaid in green is a second set of data from the same patient at a different time under a different treatment. And the amplification of amplitude and amplitude and wavelength both is a key indicator of the efficacy of the treatment. And so we're able to pull that out with these very simple empirical models to make some treatment comparisons. So that's a bit of an introduction. We've hit the several key concepts: time as a covariate, the key covariate in many problems, particular stylized classes of models, the sequential formulation being very natural, particularly in forecasting, priors. Posteriors today are tomorrow's priors, and don't think of them as immutable. Intervene. Decomposition, building models from components, breaking them apart to examine components, all in the context of univariate time series. Well, life is multivariate, so let's get multivariate. This is the same slide as I started with. EEG is multivariate. Here we've got 20 locations where the signal is probed. There's a dynamic network operating, and we were just looking at one node in that network. We'll look at some finance data, highly multivariate, of course. G networks, more dynamic networks. Where are the edges? We know the nodes. Where are the edges? Which way do they point? Are they repressive? Are they activation? Data over time on a number of nodes in a G network. And of course, over in computer modeling, many inputs, many outputs, often with lots of other structure as well. Often there's spatial structure. So let's look at, again, as I said earlier, really in the linear Gaussian world, the dynamic linear model, the state space model with constant parameters includes all of time series, all of linear time series. And if you let those parameters vary, you just get a much richer, more flexible class. And the direct analog, the workhorse of Bayesian dynamic modeling in many areas of application is simply the multivariate extension. So now we have a vector signal, and we'll have it observed with noise, or it might be the model for the data itself. Regressed on a number of past values with regression parameter matrices that may be time varying. And we can write this in a more elaborate, higher dimensional state space form, and it's useful to do that for theoretical reasons. And we can look at that theory and pull out the same kinds of ideas as we've just described. Foundational concepts of an empirical model having inside of it a series of components, and in this case, each of the nodes that represent the elements of the time series vector itself see those components differently. It may be embedded in a much more general model. As I mentioned, it may be a model for the data, or it may be a model for a piece of the data. And there may be other things going on that we want to add to that and estimate alongside the time-varying structure. So here, in this example, one can imagine building models like this, where the phi matrices represent the dynamics of the network, how the nodes are connected in terms of lagged relationships across the spatial region that the data is collected upon. In other contexts, we might be interested in thinking a little more about the innovation that drives the signal. So this is not an error for those of you that don't speak time series. This is not an error. This is the stochastic driver of the system. This is how the stochastic terms into the future get modified to predict future signals. In some cases, we might want to structure this spatially or through other covariates. In some cases, we may want to recognize that, in fact, it should be subject, at least, to some thought about whether there's time variation involved there too. And that gets us into the whole area of thinking about volatility. Okay, we've been talking a lot about time-varying parameters in the structural part, in the dynamic regressions, in the components of a time series. Well, how about the variances and the covariances? And here we've got a time series in the EEG case, where clearly the variances are changing through time. The signal is amplified, and then it's messing around, and then ultimately it decays. And the driving variances and covariances in a model for that necessarily have to be modeled themselves as time varying. In econometrics and finance, this is a picture of some econometric data. Of course, volatility is a given. And it's the be-all and end-all of decision-making systems in finance. So let's go there. Let's look a little bit at that. Let's talk about high-dimensional socioeconomic or financial data. Start at the bottom. Everything as a tutorial, I've been talking a lot about linear and Gaussian models. Of course, the concepts of time as a covariate, the concepts of decomposition, the concepts of forward analysis, sequential analysis, and intervention transcend those that special, canonical special case. Multivariate time series in many areas come as counts. But we'll stick with linear Gaussian models for the examples. In econometrics, we very often build structure into these models. Things are very often hierarchical. We might have a collection of dynamic models for different subsets of a time series that are then linked together in some form of hierarchical model. So one can imagine thetas being linked together through time. They're time varying, but they're also linked together through hyperparameters that themselves would be time varying. In finance, when one is interested in really characterizing volatility for understanding, but primarily in order to improve forecasting and to improve decisions based on those forecasts, modeling of covariance patterns and of joint structure in a distribution that varies in time beyond the mean, beyond the usual kinds of regression, is fundamental. So we'll look a little bit at this, again, looking at a covariance matrix of a state space model. This could be any one of the above models we've talked about, and I'll show you some more in a second. We'll talk about the residual, the unpredictable part, if you like. We'll think about a financial time series of returns or prices on assets. This is the best we can do to predict, and this is what we've got left, and by golly, we know that there's a lot that is left and that we better adapt to changes in it if we're going to do anything sensible in terms of forecasting and decisions. And now the covariance matrix is explicitly time varying. This is a foundational slide. For over 25 years, people have been using multivariate stochastic volatility models. The first was conceived in the Bayesian literature as a model for really a random walk for covariance matrices. More later models have refined that to autoregressive-like structures of various kinds by going inside the covariance matrix in different ways and building factor structure that's varying in time. But the fundamentals, the foundations really are all the same. We're interested in some form of time series representation for covariance structures. A latent factor version is very much akin to dynamic inverse Wishart processes. You can think about this as leading to an ability to model and adapt to change in time in a covariance matrix So if you can do that, you can pull it apart with a principal component decomposition and look inside it at principal components or principal factors as dynamic sub-processes that are implied. Or you can think about directly modeling the covariance matrix, so the variance matrix of the new term here, with some kind of linear factor representation where the factor vector F and the factor loadings matrix B are themselves time varying and subject to some form of model. You put them together and you've got a more elaborate model for the time varying volatility matrix that we start with up here. So here's a picture of, two pictures actually, of just illustrating this, and this is a textbook example 2. I pulled out 10 years of historical data on several currencies. There are a dozen currencies in this time series, and I just pulled out the Japanese yen and the British pound. So these are the returns relative to the US dollar over that time period. They're volatile, and these models estimate and track, and in the very short term, predict changes in variances. And that's what we see here, standard deviations, residual standard deviations of fluctuations. And they track correlations. So if we look at, this is pre-euro, if we look at the Deutschmark and the francs, the correlation is very high. If we're interested in the pound and the Japanese yen, we'll see fairly dramatic changes, positive correlations in the main over time, but some fairly substantial changes as we go through time. And the times of the bigger changes occur at periods of time where there's something to say about what the world economy was doing at the time. They are often very interpretable. So these are just covariances, correlations, variances pulled out of a time-varying volatility matrix. And if we dig in and look at a factor representation of it, do a principal components or fit a dynamic factor model of it, we get another look at what's going on inside the data. So let's look at the yen, since we're in Kyoto here. So there are several factors inside this volatility matrix. This is a set added together. The first two factors, think about dynamic principal components, weigh differently on the Japanese yen than they do on the British pound. And so you see the ability, the opportunity to go in there and interpret these factors by looking at how they differentially relate to the time series that they are impacting. So looking at time-varying volatility matrices and using time-varying volatility matrices in models to soak up the effect of time in the second-order statistics, if you like, of the data that you're looking at, is one part of the story. The other part is that it's useful for forecasting, and forecasts are usually used to make decisions. And so now we're beginning to think a little about decision-making in a sequential learning context. Here are 4 models running in parallel over time. Simple predictive models with volatility components of the Wishart form, where at each time point, where each day in this case, we're rebalancing a portfolio based on the forecasts are then an amalgam of the information that we have in the predictive component, the way in which we're tracking over time the parameters of that dynamic model, and the way in which we're tracking and in the short term forecasting the volatility. That often is the major part of the forecast distribution. And this is just cumulative returns in terms of you put 100 yen in at the start. This is cumulative returns being tracked over time in 4 models. So volatility is, in this kind of application, is almost everything. Understanding, modeling, improving predictions of volatility. Again, the idea of appropriately attributing variation to stuff that is time varying. Here, pulling it out and putting it into the variance matrix instead of the mean. And sometimes bringing in the ideas of intervention, because if we can interpret, if we can overlay on estimated factors in volatility matrices as we track them over time, if we can overlay interpretation, understand and link back to fundamentals, in this case fundamentals in the market, economic circumstances, then that allows us to think about how to feed that learning into the next period of time, into modifying the model to potentially improve forecasts. And these kinds of methods have been used now, as I say, for over 25 years in a substantial number of areas as components of bigger models that are used in management investment. Okay. Just water my tongue. Well, everything I've said could have been said 20 years ago. So that was the tutorial. And now we're going to fast forward a little bit and just touch on just a couple of vignettes on some more recent areas of Bayesian dynamic modeling. No surprise. Data sets are getting bigger, models are getting bigger, parameter dimension is getting bigger. Boy, if the parameters are varying in time, it's infinite dimension by definition. So we need more structure. If we're going to make sense of bigger problems, we need more highly structured models, more modular models. And that's one dimension of sparsity. We need sparsity in all of its dimensions. So these are really, no surprise to anybody else. These are the three hot buttons of what I learned in Tokyo at a wonderful workshop that some of you attended in Tokyo last week at the Institute of Statistical Mathematics, is that big data is the fourth paradigm in science. Okay? I heard that from Genshiro Kitagawa in his presentation, past president of the Institute. And I had that from Tomiguchi, current president, who's here, I think. I don't think we're in that fourth paradigm yet. The fourth paradigm is big data. Okay, that's not a paradigm of science. It's what we do with the big data, how we model it, how we store it, how we communicate it, how we model it and use it that is the fourth paradigm. And we're just opening the door. We're not even starting to think about how to hold it and store it yet. Well, we're starting to think, but most of us don't know how to. So this is the fourth paradigm. I'm going to give you a few slides just to show just some snapshots of some of the kinds of application areas where Bayesian dynamic modeling is dealing with bigger data sets, bigger models, bigger structure, where the need for sparsity and structure is ever more pressing. So here, I haven't talked about spatial structure so much in dynamic models. Here's a context where spatial structure is fundamental. So high-res satellite data where on a weekly basis, if not a daily basis, one is receiving on thousands of grid cells on a lattice around the Earth. Various measures, various aerosols in this case, data sets. These pictures come from carbon monoxide from various sources on Earth. Huge data sets really being gathered at an incredibly fast rate and available and accessible. And the problems they have a bearing on are hard, interesting questions. So the kinds of dynamic models one is interested in here would then think about the data as on a lattice in a very high dimension, or as a vectorized version. In this context, this is a context of computer modeling, where physical models are predicting fluxes of CO from the Earth, from various sources. And so that's, if you like, a set of prior information that feeds in. You can treat it in different ways. We like to treat it as covariate information, because we don't believe it. We want to understand it and how it relates to the data we actually see. So that will map through to the data through dynamic parameters, and they will be modeled in various ways, state space models, random walks, or other forms of models, because time is a covariate. And we've got lots of stuff that we don't have in this model that we know has a role in influencing the data. And then the other piece here is everything that's left apart from measurement error, and that is this is a highly spatially structured problem. And if you ignore that and you fit the model, you find there's a lot of spatial structure left. So this is where there's a need for really highly structured and highly sparse models. One isn't going to be able to use Gaussian processes for spatial analysis on these kinds of scales without lots of approximations to structure them and make them more sparse and turn them into really different models. So I think different kinds of models, graphically structured models, Markov random field models, which have lots of conditional independencies in them, are the way to go there. So integrating those kinds of models into dynamic models is a big part of where, in recent times, Bayesian dynamic modeling has been going. Backing up to a more general context and thinking about this idea of sparsity then, and again, looking over the last 2 or 3 years and where things are at right now in terms of applications, particularly in time series of dynamic models. A generic model for a vector time series with some predictive information and all kinds of parameters that may or may not vary in time. I've flipped my volatility matrix now to its inverse, to its precision, the natural parameter of the normal distribution, zero mean normal, for reasons which will become obvious. And F could be any one of a number of things. It could be something that we don't know, that we just model as a polynomial trend. It could be a dynamic regression. Well, now this is a vector. Y is a vector, so this is a multivariate regression, so A is a matrix. We could have some of our favorite empirical models because we know how flexible and adaptable they are when it comes to representing stuff that we can't explain and potentially allowing us to then dig in and break it apart and decompose it to help try and understand how we might explain at least some of it. We might have latent factors, and this is becoming more and more de rigueur, particularly in econometrics. As dimension of data, the number of economic variables that you measure increases, you need to decrease dimension in the model, you need to structure more highly, and dynamic latent factor modeling, Ben Bernanke told us 10 years ago, is a good way to start thinking about that. He hasn't been using it since he stopped being an academic, for those of you that know who Ben Bernanke is. So you could take latent factors and you could model them as through various state space models themselves. And then there's what's left, the volatility matrix on its inverse scale, a precision matrix, okay? And we want volatility in there. We want something in there, okay? So multivariate time series, as they get bigger and bigger and bigger, there's various choices, various pieces, and we're still just working in a sort of linear framework. It's not really linear because everything is time varying and these guys are latent. This encompasses basically a whole panoply of models that people use. And as the dimension gets higher here, of course, the dimension of the parameter matrices gets higher. And the number of factors that you want would get higher. This will get higher. So there's an imperative to look at those as objects that you really want to constrain as much as possible. You know, it'd be great if they weren't time varying, if we could constrain to lower levels of time variation. Well, let's have the data help us with that. It would be great if we could link them together in certain ways, and sometimes we can, particularly in vector autoregressions. We sometimes link the parameters together parametrically. But overlaid on all of this then is the need for parsimony to say, well, all of this stuff isn't going to matter, that some of these parameters are going to be not going to be there, or at least they're going to be practically irrelevant. So there's a need for sparsity. There's a need for zeros in these matrices. And one of those matrices, I'll just highlight this one since it would take another hour to talk about all of the others as well. One of those matrices is this precision matrix. And this is where in the last few years there's been a great deal of interest in sparse structuring of more high-dimensional precision matrices in time series using graphical modeling ideas. So graphical modeling simply takes a precision matrix and says, let's put some zeros in it. The black is non-zero. Okay, so we've got lots of zeros on the off-diagonal of this precision matrix, which represents conditional independencies, and an opportunity to use the theory of graphical models to break down calculations into more modular pieces that link together in formal ways, but allow us to do calculations on sparsely structured, therefore more parsimonious components of the model that hopefully the data respects. Well, does the data respect it? We have to find the structures that the data respect. So now we're looking at the question of dynamic modeling where we're interrogating the structure of the model again, and that gets us back to mixtures. So there's a number of ways that, and quite a large literature now on exploring the space of graphical models, Gaussian graphical models, asking questions about where the zeros are in a precision matrix and where they are not. And every picture like this is one graph, if you like, so it's one model structure, and there are very, very many of them. And a Bayesian analysis of a model with this kind of component then very easily, naturally gets into model mixing, because we look across the space of such structures, compute posterior probabilities or approximations to them, and then average for inferences. Some examples, there are a number of examples in portfolio analysis and time series where this has been shown to be enormously beneficial. This is one simple proof of principle example from an earlier paper where the time series dimension was 346. So the variance matrix, the precision matrix, is 346 by 346. It was a selection of stocks from the S&P 500, which is this cyan-colored line down here. This is just the value of the S&P. And the blue line here was the value of a portfolio constructed like the S&P, but using a graphical model, a particular pattern of zeros for the precision matrix in a very simple multivariate DLM. And you can see it wins, it makes more money. There are other graphs in here. This is the empty graph, so independence, and this is the full graph, which is no parsimony. All of those 346 choose 2 parameters matter. And that doesn't do so well at all. This is one of a whole series of studies and a whole series of published examples that show that sparsely structuring precision matrices, and by analogy, sparsely structuring parameter matrices, time-varying parameter matrices, in the other components of increasingly large models, can help in the usual ways. Can help in terms of precision, estimation, uncertainty about the parameters that you care about that are really there, which feeds through typically into improved precision of forecasts, and also helps in terms of finding better structures and improving forecasts if you care about forecasts. We do. In some of these kinds of applications, these studies have also routinely across a range of applications demonstrated the impact, the positive impact on prediction. Here's an example of that kind. This is a very personal example because this is a piece of my own investment in mutual funds. These are 30 mutual funds from a particular company in the US. You can see this is just a little example. These are monthly data over a period of years. You can see a lot of co-movement. And what we have here is a model average over many millions of graphs, so many millions of patterns of zeros and non-zeros on the off-diagonal of the precision matrix. And the non-zero elements, of course, are time-varying. We evaluate posterior probabilities, approximate posterior probabilities, and this is a heat map of those probabilities. You can see that a lot of these edges have black. They're very surely there. There's a bit of red and yellow. There are a few uncertain edges. This is probability of 0.2 to 0.5, and the rest is white, so they're really not there at all. So this is a region of the posterior over the structure of this particular dynamic Bayesian model, structure in terms of sparsity, which is really finding lots and lots and lots of model structures that have the same components. And this graph is really a nice way of summarizing the statistical, probabilistic, and the decision implications of building sparsity into dynamic models in this kind of context. It's a nice picture. What we have here is just 200 graphs. These are a collection of 200 higher probability graphs. Log probability, okay? So these guys up here are really dominant. This is a huge, they're around a huge mode. These are negligible. What we have along here is sparsity in terms of the percentage of white. I'm sorry, the percentage of black, the number of edges that are in relative to the total. So these graphs all live sort of in the 10 to 15% sparse range. These are highly sparse graphs, okay? So there's a lot of zeros in this precision matrix. This fellow at the back is down here at about -1,000 on the log probability scale. It's on the back plane in sparsity. That's when you have no zeros in the precision matrix. That's not a very interesting model structure. This axis shows us risk. These models were used in one-step forecasting with the same portfolio utility function to revise portfolios and see how much money was made. And on this axis, we've got risk on a standard deviation of one-step ahead portfolios. High risk is bad. I don't like to gamble my own money. If it's in my pension fund, I don't like to gamble it, okay? Low risk is generally good. So low risk portfolios have higher posterior probability and tend to be associated with sparse graphs. So sparsity is good from both the point of view of the statistical point of view, high probability, and a piece of the decision theory point of view, lower risk, okay? The color coding is the fourth dimension. The color coding over this period of, well, we did an out-of-sample predictive portfolio analysis. Over whatever period of time we took, this shows us the return on the portfolio for each of these model structures. So red is really good. So you see, if you don't mind taking a lot of risk, you can make a lot of money with sparse graphs, but they don't tend to be very high probability. There's a lot of red up here, so there are a lot of high probability graphs that make money that are low risk. And these are interesting model structures. There are also some graphs up here that don't make so much money that have high probability. So it's not a given that posterior probability is the way to search over model structures if what you want to do is select a model or select a few models. If part of what you're interested in is using these models for decision making, then you've got to factor in the utility functions as well. And that can lead you into different parts of the model space. Okay, two more. Let's see. Where's my chair? Oh, 10 minutes. That's good. That's good. I'm on time. A couple more slides then. I'm now fast forwarding even more to just to point out a couple of areas of Bayesian dynamic modeling that are topical, in that I know a lot of people are interested in them and working on them, and I find topical. On the sparsity theme, so what we've been talking about there is taking a model structure, whether it's an autoregressive parameter matrix or the precision matrix of a volatility model, or a dynamic regression coefficient matrix, or something else. And as dimension explodes, we want constraints, and some of those constraints will be saying, let's put zeros in there, let's find out where the data doesn't argue against that. Well, that's a good strategy, and we all do it. We all do Bayesian model selection and use prior distributions that wipe out parameters to zero if they don't look interesting. But in a dynamic context, in a time series context, there's time as a covariate. You might have a model where you've got a particular set of zeros in a precision matrix, and it's been working fine. But circumstances change, and you haven't got a model modification, and you haven't got additional covariates or information that has allowed you to anticipate that change. And a correlation pattern changes that suggests a different pattern of zeros in that precision matrix. A zero suddenly pops into life and takes a non-zero time varying value. Or something that was important practically, I try not to use the term significant, that it appeared in the model and the data liked it and it was relevant, it influenced predictions, suddenly becomes irrelevant. This is the notion of time variation in sparsity, and this is the picture. So here we might have some regression parameters or a precision matrix where at different periods of time we want different patterns of zeros. And we want some formal model, time series model, that allows those things to naturally appear. So you can think about switching mechanisms of various kinds, but as the dimension gets higher, typical methodologies of switching mechanisms are really challenged to represent this notion. So that's one topical area. In two of my earlier slides, I had pictures, this particular, or a vignette, a cartoon very similar to this. This is another area where we are seeing more and more interest in dynamic modeling. gene networks, cellular networks, looking at networks of genes within cells, and also networks of cells, of course, and other kind, not just genes, but other molecules. Well, we often start with at least a notional class of mathematical models or biochemical models, and then, of course, quickly abstract to the statistical level, because everything is in discrete time anyway, in terms of data. And one is interested in then fitting a highly nonlinear model, which has typically an overlay that we're interested in the question of understanding sparsity patterns. Because biological network models like this are drawn very often with some of the edges and the arrows in there well understood to be real biochemically and potentially functionally, but very often also it's a hypothesis. The network structure itself is also of interest. So the same general questions of looking at time series data where things are varying in time, parameters that represent strengths of association on arrows and arcs in pictures like this are the thetas that will be varying in time typically because of the context in which the cells are growing and all of the other things we don't have in the model. But we're also interested in the sparsity structure too. There's lots of other interesting questions here. There are spatial aspects. I'll talk a little more about latent states and missing data in a minute. When one discretizes differentially, when moves from continuous to discrete time, typically these models will be built on a very fine discrete time scale, and data is on a much cruder scale. So there's tons of missing data, tons of latent variables, tons of latent states that become part of the state variable that we're now dealing with in the analysis. Imaging is important, and to get data, that's a whole another story. Let me say a word about computation. This is a foundational issue. Until I fast-forwarded, I was still back in the 1980s. A lot of the story was analytic computation till the end of the 1980s. Since then, as we all know, life has changed. We use simulation. I got up there synthetic futures. I use the term synthetic rather than simulated a lot, particularly in time series. And in other process modeling contexts, don't look at prediction by computing means and variances and other things. Just simulate and ask questions. How do those synthetic futures compare with the real data, just subjectively? So we've had 20 years of, more than 20 years of MCMC, and some of you will know that this really had a big impact on Bayesian dynamic modeling, as it did on all areas of Bayesian statistics. Some of you will know about Viterbi-style algorithms, forward filtering, backward sampling methods for simulating in linear Gaussian state space models, extensions of that to mixtures of models of various kinds, of the two kinds I alluded to, mixtures in models in parallel and models that get mixed up in different ways at each time point. Of course, it's been revolutionary. We've had more than 20 years of sequential Monte Carlo, the foundational concept of learning in time sequentially. We may care about the past for analysis, retrospection, to understand and adapt our model for the future. But we're interested primarily in moving ahead, updating posterior distributions on time-varying quantities, forecasting ahead, seeing data, and moving along. So particle filtering has been around since the 70s. Some of us didn't know that until the end of the 80s in engineering. Particle learning, ABC methods, a whole variety of methods have come along since, and they're all being applied to dynamic Bayesian modeling in time series as well as other areas. And we use them all the time. And some of us are involved in trying to improve them. Whoops. This is open territory from the point of view of computational methodology. We've got lots of very, very useful tools in our computational toolbox for dynamic Bayesian modeling. But they're really highly challenged, and they're particularly challenged by the coming fourth paradigm. The dynamic networks in cell biology example involves a small number of genes, but many, many missing values of the expression of those genes in the discrete time model. So there's lots of latent states, high-dimensional parameters, high-dimensional time-varying parameters that have to be imputed. There's strong structure, there's strong priors. Part of the model is the priors. But the imputation of latent states in time series and in spatial processes, and in the combination of the two, is something we don't know how to do well in any general sense. The same is true of sequential Monte Carlo. We'll hear a lot about that, I think, later today. I think Chris Robert's talking some about computation, and I know Arnaud Dosset has one of the invited lectures later this week on particle filtering style methods. And we'll hear about the latest and greatest. But it's fair to say that some of the more challenging issues that we faced 20 years ago when both MCMC and SMC were being imported into dynamic Bayesian modeling and time series and spatial process modeling and other areas at the same time, are still faced today. Problems that are forced by the increasing scale of the models in particular really are open questions. Well, that about concludes what I had to say, a bit of a historical perspective, Valencia-style tutorial, and then fast forwarding and just highlighting, buttoning on a couple of things from the last several years. Just coincidentally, there is a collected volume about to appear that was edited by Paul Damien and David Phillips, and this was a collection of chapters that was solicited for a volume in honor of Adrian Smith. And coincidentally, there's a paper in that that's got the same title as this tutorial. And even more coincidentally, if you're interested in some of the things that I've talked about, it pretty much follows that paper. There's a lot more in the paper. If you want to dig a bit deeper and haven't already, shameless advertising for a couple of books, a very big one, but an older one, and a slim one, but that's packed with lots of goodies as well as all of the old stuff. And I should mention, not only because we're here in Kyoto, but two very important books in the panoply, under the umbrella of Bayesian dynamic modeling. This was a very important book, I think 1987, by Genshiro Katagara and Will Gersh, on the topic of time-varying order regressions in particular, although they didn't know about the decomposition stuff in those days. And another book that relates back to, in particular, work of Akaiki in time series, which has had an impact in the evolution of the discipline in a number of ways. With that, I'm done with the presentation, and you might want to switch the video off now. Oh, hang on a minute. Not quite done at all. Not done at all. This is ISBA 2012. Well, it's about to start. And I thought I'd point to a couple of dynamic Bayesians. There are a couple of talks really that relate to some of the themes on the vignettes on the later stuff that I mentioned. Local boy Joshi will be talking about dynamic sparsity. So I opened that up as a topic. I think it's a critical topic, and a number of groups are interested in it that I know of, and I'm sure that there'll be others here that will have a view on problems of that nature and how to approach them. Another local boy, Ryo Yoshida from the ISM, is talking about sparsity and dynamic networks, again related to a degree to biological applications. Johanna Manolopoulou is talking about dynamic models in biological systems with a spatial component, all using dynamic nonlinear models, but time as a covariate is pretty important there too. I gave you my view of where we are with sequential methods in dynamic models currently, and Fernando Bonassi will be, among several other people I know at the meeting, making a presentation on some advances in sequential Monte Carlo methods synthesized with ABC, which needs a new name, specifically for state space models. And harking back to some of the multivariate studies, Raquel Prado, as is her wont, will be showing some of her latest work on multivariate dynamic models that some of you may be interested in. And just sitting outside, I was tinkering with my slides, and I looked through the book, and I just scanned through quickly for the word dynamic. And there's more talks and papers at this meeting. So it's certainly a timely meeting to have a tutorial presentation on the topic. And I look forward to seeing, well, as many of these as I can get to, hopefully all of them. Thanks for your attention, and have a great ISBA 2012.